very, very stable there. It will spend 90% of a star's life will be sitting in that state there, hydrostatic equilibrium on the main sequence. So you've probably heard our star lasts about 10 billion years of the main sequence. So that immediately tells you when it's done and dusted there, the remainder of its life is going to be just a quick billion years, so 10%. Key principle, bigger the mass, higher pressures and temperatures, burns fuel a lot more quicker. And a good analogy, you have a rip-roaring bonfire, raging away, and you throw a log on it, 10, 15 minutes, that log's just burnt up. When you go to bed at night, you let the fire go down a little bit, just to keep the house a bit warm, and for the morning you throw a log before you go to bed and put a screen over it and stuff. Get up next morning, 8 hours later, that little log is still just quietly smouldering away. It just doesn't burn so quickly. I use that analogy for metabolic rates too. Everyone should have breakfast, single most important meal of the day. Get that metabolism roaring. Anything else you eat for the day will just burn up. Versus if you starve yourself and metabolic rate drops right down, everything you eat just turns to this stuff here. Another little analogy that I can use day to day. So bigger mass, higher pressure and temperature, burns fuel quicker, and that's what it's all about. They have big stars burn out quickly, have big, great, big, bright, flashy lives, but burn out quickly. Much like Hollywood stars. Okay, so we're still on the main sequence. What does this look like on the Hertzsprung-Russell diagram? As I said, just recapping, by definition, a star with hydrogen fusing into helium at its core, that defines a main sequence star. We mentioned it's got all luminosity class 5. So if you ever see the name of a star given with a spectral class, and it has a Roman numeral 5 after it, that immediately tells you that star is on the main sequence. And it starts up here, the main sequence, in the top left-hand corner, high temperatures, that goes up to over 50,000 degrees, up to 100,000 degrees, high luminosity, a million times as bright as our sun, and it quietly trickles all the way down here to these really low temperatures, less than 3,000 degrees, and really, really dim. And they've put on here, in white, the masses of the stars. And do you notice there's a pattern there? All these low mass stars are all in this corner over here, dimming really dim, really cool, and as you go up to one solar mass, namely our sun, 1.5, 3, 6, and so on, you're getting a brighter, brighter star and a hotter, hotter star, the bigger the mass is. So just recapping your principles here, the larger the mass, the bigger, hotter and brighter it is, the faster it will burn its fuel, the shorter the life on the lifespan on the main sequence. In fact, we even put them here. See, here's our sun, about 10 billion years. This spends another 10% longer on the main sequence. Look at these stars. The further you go up, the bigger they are, the hotter and brighter they are, but look at their time span on the main sequence is just dropping right down. Because the bigger, they got more mass, so they got more gravity grinding down, so the temperature in the core is higher, so it burns that hydrogen up so much quicker. So stars being 90% of your life on the main sequence, that also immediately implies 90% of stars in the galaxy are on the main sequence. It just makes sense, it just follows. One of my last slides tonight, got some food for thought about that. What are you seeing when you look up at the sky? Yeah. Each successive, another little principle that you're about to learn is each successive stage of evolution for each star gets shorter. In other words, the main sequence is 90%. As you see, we're going to go to the red giant phase, to the horizontal branch, the asymptotic giant branch stage. Each of those stages is proportionally shorter and shorter and shorter. So a star spends most of its time stable, and then quickly it just snowballs and snuffs itself out. But in an interesting way. So what's going on inside the main sequence star? So it's burning up this hydrogen by fusing it. So it's creating helium, and the helium sinks to the centre of the core. Why would that be so? It's heavier. Yeah. Helium is two neutrons and two protons matched up against a proton. It's a lot heavier. Heavier things sink to the middle. So it's a gravity sink. So this is relevant where I'm leading with this. I'm not telling you any sort of know anything, just for the sake of it. This is very relevant. The helium starts sinking to the centre of the core because it's heavier. Until the core becomes more and more and more predominantly inert helium. Inert meaning it's not fusing, it's not reactive at the moment, the temperatures aren't high enough. So what happens next in the core, in the middle of the core? Core fusion stops. It just builds up more and more helium, just sinks down to the middle, more and more, and it gets to a point where the core is mostly filled with inert helium. Fusion just comes to a grinding halt. So what happens next? Remember, that was propping the star up. So the star becomes a red giant, but how does it do that? Well, the core of inert helium is not hot enough for nuclear fusion yet. The pressure and the temperatures, as we've talked about, in a star the size of our sun, about 15 million degrees. That burns up the hydrogen, but it's not hot enough for helium. So what happens is the helium will concentrate around here in the core, but you get a shell still of hydrogen still burning away outside the outer parts of the core. So what happens next? So you're left with this inert core, hydrogen, of helium rather, with hydrogen and shell still doing nuclear fusion, but a little shell surrounding the core. What happens? Two things happen. The inert core can no longer match the force of gravity. So what happens, starts contracting. You know it was propping itself up before, so it starts contracting and getting squeezed tighter and tighter. That acts to raise the pressure and the temperatures in the core, start moving on from that. We're sick of 15 degrees Kelvin. Hot enough, baby, let's raise it. Pump up the jam. So we're going up and up and up. The second thing is, this outer shell of hydrogen fusion that's still going on starts pushing the layers, the outer layers of the sun outwards, which in turn increases the size of the star. So what happens then when you start increasing the size of the star? It's again two things that happens. As something gets larger, and you remember from our formulas from a couple of months ago, that luminosity is related to size. In fact, it was pi r, 4 pi r squared. So naturally, if something's getting bigger and bigger, it's just going to get brighter and brighter and brighter. So the star's luminosity goes up, and you think to yourself, okay, so we're moving up the diagram now, the HR diagram. But the other thing that happens is you've still got that standard temperature inside the sun, but suddenly you've got a bigger surface area to spread that energy over. So per square area, say per square metre for example, must get cooler. You've got the same amount of energy spread over the wide surface. What happens when anything hot gets cooler? It goes redder. So suddenly you've got a red giant. One mighty big large star, and it's red. Because of why all this contraction's going on at the core to raise the temperature, it's no longer fusing, all because of this hydrogen shell burning. We're going to see a lot more of shells burning shortly. So where on the HR diagram is there? Yep, and there's our friend Betelgeuse right up here. So it started off somewhere here. It started getting cooler because it was expanding. So it started getting cooler, but it was getting brighter because of that. So it headed up this way here. Here's Betelgeuse. A lot brighter and a lot cooler in a red colour. Hence the name red giants. Higher mass stars are called supergiants. In fact, Betelgeuse is a supergiant. You probably remember some of the names of giants like Aldebaran, Pollux, Arcturus, and so on. So that's where those babies sit, and you now understand why. You know why they've just left the main sequence and headed up there. That core is not fusing, it's contracting, but more importantly, you've suddenly got an outer shell of hydrogen that's burning, that's expanding the star. So let's just for a little bit of lightheartedness, just have a relaxation. Let's have a look at how big they are. That's our sun there, as it is now as a main sequence star. When our sun becomes a red giant, that's how big it's going to be, the radius will be 100 times bigger. And where are we going to fit in all of that? throughout, here's our little sun, that little dot there. And there's some red giants that we saw before, Arcturus and Aldebaran that we saw in the HR diagram. But look at Betelgeuse. Look at Antares. These are some red supergiants. Just bigger versions of red giants, essentially. Why is that? Because they've got a bigger mass, which you immediately know they're going to have shorter lifespans. Betelgeuse, if you plonk that with the sun as in the middle of our solar system, it would extend right out to Saturn's orbit. Huge. That's a picture from a real picture of Betelgeuse from the Hubble Space Telescope. So let's move on. So we've moved on now. We've had the main sequence, nice, happy, stable phase, burning hydrogen in the core, sits there for 90%. Runs out, outer shell of hydrogen, puffs it up to a red giant. The next stage becomes what they call a horizontal branch stage. And that's when the core temperature then does, in that core, it was contracting. The pressures and the temperatures go up until it reaches 100 million degrees in there. Whammo! Helium says, yeah, we're ready to rock and roll, guys. This is our temperature. Helium fusion kicks in, and helium fuses into carbon and oxygen, the core of that star. Here's all the little things going on here. Helium forming into beryllium, which is very unstable, and that's a really interesting talk in itself, carbon and beryllium states and so on. Carbon and oxygen forms. And that's actually called, these are called alpha particles. It's called the triple alpha process. You might see that term, the triple alpha process. It just means three heliums are getting together, joining up, having a party, fusing together, carbon, which then can go on, called oxygen, with the liberation of energy so that core starts to stop contracting. So let's have a look. What's going on inside one of these horizontal branch stars? Core temperature's reached 100 million degrees. And in an analogy before, you've got a little, helium converting carbon, oxygen, helium into carbon and oxygen here. You get a little helium intershell here. It's not quite burning yet, it's just sitting there. But you've still got this hydrogen shell, outer shell, that's busy still fusing hydrogen into helium. And then you've got the envelope around it. So that's what's going on inside. So let's have a look what sort of implications of that. So this is where it sits up in here. There's your red giant phase coming up in the red giant branch. The helium kicks off in a big mighty flash. We don't see a flash, it happens inside the core, it just suddenly kicks in. You lose a little luminosity, but the star then, because you've got nuclear fusion going on, starting to push the star back out again and starting to drive that hydrogen, that hydrogen shell out of it, the temperature starts going up again. So the star on the HR diagram starts moving across here, and it's called the horizontal branch. And I know what Keith is probably thinking. I know he's going to say, I know, Keith, what you're going to say is, why that little drop of luminosity there? Well, that's up and up. Keith's going to ask me this one. And it's because as the nuclear fusion kicks in of helium to carbon and oxygen, the core expands a little bit, and it pushes out the hydrogen shell a little bit and increases the volume, which just very briefly drops the temperature and pressure in the hydrogen burning zone. So the hydrogen burning rate just drops off briefly for a while. And of course, it's the hydrogen burning that pushes the star out and create that high luminosity to increase its size. So that's why the luminosity just drops off. A little bit of minor detail. But the bottom line is you see the star moving its evolutionary course across here. Then you come to the crossroads. For stars less than 8 solar masses, it then approaches the asymptotic giant branch phase, where the core is exhausted of helium, but it's not hot enough for carbon and oxygen to burn. The temperature doesn't get much higher than where it is now. Why? Because it's only got 8 solar masses or less, and that's all the gravity that the gravity can muster up. So the inner core, no fusion occurs, it starts to compress itself. So you start getting a core compressing of inert carbon and oxygen. Meanwhile, and here's the catch in this phase, you start getting an outer shell now not only of hydrogen burning, but you get an outer shell of helium fusion going on as well, which means the star now, woohoo, it's expanding even more. Here it is here, that's the star, AGB standing for abbreviation. It's expanding up the core, you've got your inert core there, and you've got your helium burning shell, and then your hydrogen burning shell. Whammo, that really pushes up the size and the luminosity of the star. And here you can see them here. Here's the asymptotic giant branch. Never mind the going up there, that big luminosity of the helium. Look at this baby, she rockets up. So it's a much lower temperature, same principle as before. It's expanded hugely in size, so it's much, much brighter, but its temperature's also dropped as well. They're called evolutionary tracks, and every star, you can see here, I've illustrated on this one here, every star of a different mass has got slightly different tracks. So, the other interesting thing with these stars is that because you've got these two shells of nuclear fusion going on in the shell now, further out, and these stars are whoppingly large, which means their gravity in those outer parts is going to be much, much less because you're further away from the core of the star. So they've got a very low gravitational force up here, and they've got nuclear fusion going on their shells. They become very unstable. The outer shells become unstable, and they just start firing off and shedding big layers of the stars. Because they're so far away, the radius is so big, they're losing that gravitational attraction, and you've got nuclear fusion going on there to boot. On top of that, in this phase here, you get a couple of, there's actually quite a few various cycles, but you get two key cycles that are called dredging, where the whole thing of convection drives down and scoops up some of that carbon and oxygen that's going on down near the core regions and brings it up to the surface of the star, up to those outer layers that then get cast off. And that is the key source of carbon and oxygen in the universe. And of course, what are the third and the fourth common elements in the universe? The third is oxygen, and the fourth common element is carbon. What do we need for life? Oxygen and carbon. That's where we got that from. You can say, thank you, asymptotic giant branch stars. They were the ones who gave life to us. I think they're very right. Okay. Then what happens is the shedding goes on and on and on. You start getting what they call a white dwarf in the core. So that's the little core, inert core of oxygen and carbon. And here, you've probably all seen these pictures before. And these are all the outer layers, all being shedded off. These carbon and oxygen cores are very, very hot. So they radiate high energy radiation, which then ionize and illuminate all the gases that are shedding themselves off these outer layers. And that's where you get these lovely big pictures. I'm sure you've seen these pictures loads of times in books and on the internet. That's what they are. They're asymptotic giant branch stars, less than 8 solar masses, that are then become unstable and shedding all their carbon and oxygen outer layers, leaving a hot white dwarf in the middle. And that's what's going to happen to us. So what happens to stars greater than 8 solar masses? They have enough mass to just keep pushing on. As opposed to the smaller ones, couldn't fuse the oxygen and the carbon. You need up to do that, you need up to about 600 million degrees to do that. These guys, higher amounts of mass, higher gravity forces, raise the core temperatures, they get up to these temperatures, and they're able to do a succession of just fusing, and a series of fusions right up to iron. Each time they're doing that, they're successively hitting elements, they're producing more and more energy, they're blazing away, they're having a great time. They go through the same phases, but they suddenly get to an iron core. And the nuclear binding energy of iron is very, very high, such that it actually gobbles unique energy put into the system. You start fusing iron, rather than liberating energy to drive the star, it actually absorbs energy. So what happens? The whole star just collapses on itself really, really quickly, hits the inner core, and just rebounds again. That's when you start getting a supernova explosion. That's all the supernova explosion is. Just these big outer layers, suddenly there's no force anymore, gravity wins the race, hits that central core like hitting a brick wall and just bounces off it. and just rebounds and displays out these beautiful big supernova remnants. What happens to the core if the star is 8 to 20 solar masses? It becomes a neutron star, which we'll talk about in a later month, and a supernova remnant. If it's more than 20 solar masses, as a rule, it'll turn into a black hole, a supernova remnant. So we'll talk more about that another time. So yeah, stellar evolution in a nutshell. Average star, red giant, falls into white dwarf planetary nebula. Your big stars, red supergiant, like the Betelgeuse, it goes supernova and comes into a neutron star or a black hole. And of course, that's us up there. Mr. and Mrs. Average. Average is good, isn't it? We're saying in the car down today, when you get to a certain age, when you're in your 20s, you want action. Get to a certain age, and boring is so good. Okay, so let's bring all this together now and see Hertzsprung-Russell diagram is a powerful tool. Here it is here, you've seen this diagram before, your temperatures, your luminosity. So you look at a star in the sky, which we looked at, what it looked like in the sky, you picked it out and named the star. Oh, that's Betelgeuse. We saw the sun today, well, no, we've got overcoats, don't we? We did see the sun today. But you might say, well, where are they in their evolutionary tracks? And what's going on inside them? Well, Betelgeuse now, you plot it, you go in the literature and you find out, you think, well, this is how hot it is. This is its luminosity. You might think it didn't have to get a luminosity right now, but anyway, it's red. So, the red supergiant. So that tells you, oh, that's in a certain part of the diagram for the red supergiant phase. I know what's going on inside there. It's just about, you know, it's got an inert helium core, but the temperature's approaching a million degrees Celsius. It's about to have an helium flash kick in. That's where it is, and it's expanding because it's got a hydrogen shell. You've worked that out yourself just by looking up into the sky. But the sun, you might once again, you find out, you go on the internet, dare I say, Wikipedia, who said that? Anyway, you go on here, you find it's got a surface temperature of 5,800 degrees, and it's got a luminosity of 1 solar, so it's right here. Yeah, oh, that's in the main sequence. I know what's going on inside that star, the sun. It's hydrogen fusion, and it's in a happy, stable state of hydrostatic equilibrium. You work all that yourself. So tonight, in our chat, I've shown you that stars are classified by their temperature and their luminosity. Stars evolve, and it's the mass that determines how they evolve and when, how quickly they evolve. The Hertzsprung-Russell diagram plots the temperature and the luminosity. And it's a very powerful tool to determine what stage of evolution a star is at. Now, we'll have our 30-minute movie lecture. Good. This is Professor Cliven Stassen, who I was privileged enough to actually attend one of his talks in Nashville a couple of years ago. Got to chat to him afterwards about the making of this whole series of talks that he did. Or if you could turn for copyright, all that sort of jazz.
Of course.
If you could flick it off, that would be great. Thank you. So that's actually 32 minutes.